So for this problem, you can look at problem number 6.46 also, because there we have discussed when the nucleus is not fixed, how do we write our radius and energy. So, but we will discuss it here also. So for that, we must know that when we derived the equations, then the nth orbit of R was inversely proportional to mass of electron. So the revolving electron, right? Energy is proportional to that, and mu reduced mass is m1 m2 upon m1 plus m2. So we have discussed that a little bit in 6.46. Now in this problem, we need to find the separation between the particles, that is the modified Rn, the corresponding binding energy and wavelength of first line of Lyman series. If the system is of mesonic hydrogen atom whose nucleus is proton in a mesonic and electron is replaced by meson whose charge is 207 times more that of electron, whose mass is 207 times more and charge is same as electron. And second case, a positronium consisting of an electron and positron revolving around their common center of mass. So both of them have equal masses but opposite charges. So for that system, what will be the distance between them, binding energy and the wavelength of first line of Lyman series? So when we derive these equations for the Bohr, so if you forget about the constants, what we know is that the radius in that case was inversely proportional to mass, and energy was proportional to mass again of electron. So let's start from there. So what we derived in our original equations is Rn was proportional to 1 by Me. And in our new case, Rn is proportional to 1 by reduced mass. And we also derived for our original equation that Rn was equal to 0.529 n square by z. So if you just divide these two, you will get the modified Rn is 0.529 Me by mu n square by z angstrom. So similarly, we will do it for energy. So original energy is proportional to Me and energy is 13.6 z square by n square. In our modified case, energy is proportional to mu E, and therefore if you divide these two, you will get En is equal to 13.6 mu by Me z square by n square. Wavelength. So lambda is proportional to 1 by Me. That gives, from here we derived this. In our case, lambda is proportional to 1 by mu E, which gives the modified lambda as this. So again, you just divide these two and you replace this lambda by this and you will get your modified lambda. So now first case for the mesonic hydrogen. So in that system, M1 is equal to 207 times Me and M2 is equal to 1837 times Me. So we'll just put that value from here. We'll find the value of mu by mu E, which is this. And then we can put this value mu by mu E in this equation. And we'll put N as 1 and we'll put Z as also 1 and we'll get our answer. And in B part for the positronium, so M1 and M2 both are equal and their masses are same as mass of electron. So mu by mu E becomes 1 by 2. So again, when we want to find the radius, we'll put the value of mu by mu E as 1 by 2. So our radius will be twice of the original radius. So twice of 0.529 angstrom. And similarly, energy also we can calculate. So we'll put the value of mu by mu E as 1 by 2. And our Lyman series line will have the energy of 13.6 by 2. Okay, so what we have discussed, we have written here. And similarly for lambda also. So in lambda, mu by mu E will be in denominator. So this mu by mu E 186 should be in denominator, and in this case, it will be reverse of that. So 1 by 186 and here will be 1 by 2. So this will give our modified answers of the distance between the particles, the binding energy of the electron, and the wavelength of first series of Lyman series. All right.